Alright, today we're looking at direct variation, and in our first section for this we talked about rate of change and we talked about slope. And direct variation is just a specific type of a rate of change or a specific type of function. And so for direct variation, our definition for it is that it can be written in this specific form. And so the form that can be written in is that y is equal to k x. And so all direct variation equations can be written in this form, y equals kx. And so a couple of things to note about this form. One, the first thing that we do is that we solve for y. So here in just a little bit when we're doing some examples, and we're trying to decide, is this a direct variation equation? Our first step is we solve for y. Y needs to be by itself. And then secondly, we have k, which is the coefficient here in front of x. We can solve for that. We'll talk about here in just a second. And then there's nothing after the x, like there's no y-intercept, nothing comes after that. It goes through 0, and so we'll again look at that and make sure that we're clear on what that looks like. But that's what makes it a direct variation function. We solve for y, we have this constant slope, our rate of change stays the same throughout, which makes it a straight line, and then right here goes through the point 0, 0. And so therefore there's nothing written after our x. In order to find k, k is the coefficient that goes in front of our x. And so in order to find k, we can solve for it. And our direct variation equation looks like this, y equals kx. So if I wanted to know what k was, I would need to get rid of my x. To do that, I would divide both sides by x to get rid of it. And so I could find that k is equal to y divided by x. And again, it's constant. It stays the same throughout. It's always going to be y divided by x throughout my entire equation if it's a direct variation equation. So as we look at the graphs of direct variations, here's two that are true, like these are direct variation functions. And so a couple things again to note. First of all, in both of them, we have a straight line. Our straight line tells us that our slope is constant, like it stays the same throughout, it never changes, and creates that straight line. And then secondly, our thing to note is right here, that it goes through 0, 0. And again, in our function or in our equation, what this means is there is nothing that is written after the x. And so these are the two things that are true of direct variation functions, straight line, so we have that constant k, and then it goes through the point 0, 0, nothing is written after our x. So identifying direct variation, again, every time here's kind of our overarching goal is that we're going to solve for y. Once you solve for y, we can tell whether it's direct variation or not. So in problem number A, we need to get rid of the 7 by dividing both sides by 7. And so we end up with y is equal to 2 over 7x. There's our final equation. And so is it direct variation? Yes. We have a constant slope, and so 2 over 7 is our slope. We have no y-intercept, nothing's written after the x. So yes, it is direct variation. For example, B, we're going to subtract 4x from both sides to get rid of it. When we do that, we have 3y left over here. Is equal to, and since these are not like terms, we can just write both of them, negative 4x and positive 8. And then we divide by 3 to get rid of it, so we can get y by itself. We end up with y is equal to negative 4 over 3x plus 8 over 3, since we have to divide them both by 3. So there's my final equation. For this one, we do have a constant slope or a constant rate of change. It's negative 4 over 3. However, no, it's not direct variation. Why? Because of that. It doesn't go through the point 0, 0. In fact, it goes through the point 0 and 8/3. So therefore, not direct variation. In order to write our direct variation equation, we first need to solve for k. And so my direct variation equation always looks like this. Y is equal to kx. In this case, we know what y is. It's 35. We don't know k yet. We're going to figure that out here in just a second. But we do know what x is. It's 5. And so now we can solve for k. We can get rid of this 5 by dividing and dividing. And so we get k is equal to 7. And now we can take that and plug it back into our original problem. And so our direct variation equation is y is equal to 7x. Now, the second part of the problem says, so there's our direct variation equation. Second part of the problem says, what would the value of y be if x was 9? So now we can solve for y by substituting in 9 for x. And we find out that if x is 9, then y is equal to 63. So there's my direct variation equation. Found k. Replace it in my original problem to get my direct variation equation. Now from here I can solve for any x values that it's asking about. Alright, last example. It says this, the weight on Mars, y. So in our problem here, whatever the weight on Mars is, we're going to represent it with y in our problem. Directly varies with the weight on Earth, which we're going to represent with x. The weights of science instruments on board the Phoenix, Mars, and lander on Earth and Mars are shown. So here they are. We have weight on Mars. We have weight on Earth. And again, this is y. This is x. Okay? What is the equation that relates the weight in pounds on Earth x and the weight on Mars y? And so again, first step is we need to figure out what k is. So we have y equals kx. There's our direct variation equation. And then instead of y, we're plugging in 50 equals k. And instead of x, we're plugging in 130. And then we need to solve for k, so we divide both sides by 130. And we get that k is about equal to, if we solve it as a decimal, it would be 0.38. If we wrote it as a fraction, it would be 5 over 13. So there is k. And if I write the new direct variation equation, it would look like this. Y is equal to 0.38x. So there's my direct variation equation that relates the weight of Earth to the weight on Mars. And then we need to graph it. And so if we're going to graph it, we can just pick some points to plug in here for x and y. Easy one to always pick is 0. So we replace x with 0. 0.38 times 0 gives us 0. And then we can plug in a few others on the graph here. We've got 25, 50, 75, 100. So let's just go ahead and put in 50. And when we substitute that in for x, and 0.38 times 50 gives us 19. And we can substitute in 100, an easy one. 0.38 times 100 is 38. And we can create our table, and then we're just putting these points on the graph. So we have 0, 0, and again, 0, 0 always necessary for direct variation, so it has to have that point. And then we go over 50 and up 19 and put our next point. And then we go over 100 and up 38 and put our next point. And then we're just drawing our line through them. Again, if it's not a straight line, then it's not direct variation. But this one is straight line through the point 0, so it varies directly. That's what our line looks like. Again, direct variation, our equation for it, every single time we solve for y, we get y by itself. Y is equal to k, which is our rate of change. It's always constant throughout. X, and then there's nothing after the x, because it's always going to go through the point 0, 0.